In our previous video, we looked at how to analyze and create sampling distributions for means. In this video, we will be looking at how to actually construct confidence intervals for means when sigma is known. So the difference here is that in these cases we don't know our parameter, but we're going to create an interval in order to estimate its value from a sample. So let's remind ourselves how to construct confidence intervals for proportions. So when we did that, our population parameter was p, but when we construct confidence intervals, we don't know the population parameter, so we're not going to be using p at all. In that case, we use the sample statistic, a proportion we got from a sample that we took, and we call that statistic p hat. The center of our confidence interval was always p hat, and around that center we constructed a margin of error based on our sample size. And that margin of error had a formula of z star, or a critical z, times the square root of p hat times 1 minus p hat over n. And that square root expression is from the standard deviation of a sampling distribution for a proportion. So that's where that came from. And we had to remember certain important critical z values. Specifically for a 90% confidence interval, the critical z is 1.65, for 95% it's 1.96, and for 99% it's 2.58. You're going to see in a little bit why I'm reminding us of those values. If we're constructing confidence interval for a population mean, we're going to be doing this assuming that we actually know the population standard deviation sigma. I will explain why at the end of this video. But the population parameter is normally called mu, as we discussed in the last video. But again, this is a confidence interval, so we're going to assume we don't know mu, so we're not going to be using it. Instead, we're going to use the mean of a sample that we take, and that statistic is called x bar. So that's how we represent the mean of a sample as opposed to a population. The center of our confidence interval, like with proportions, is going to be our statistic, x bar. The margin of error for a sample size n is going to be based on the standard deviation for a sampling distribution for means. So it's going to be z star times the quantity sigma over the square root of n, which you should recognize from the last video as the standard deviation of a sampling distribution. And since these sampling distributions are normal, the z star values are the same as those for proportions. So let's actually look at a practice problem to see how we would do this. So suppose it is known that the population distribution of heights of adult women has a standard deviation of 3.5 inches. A random sample of 200 adult women has a mean height of 63.4 inches. Find and interpret a 95% confidence interval for the population mean height of adult women. So you can see here that we're saying that we somehow know the population standard deviation is 3.5 inches, even though we don't necessarily know the population mean. So let's get our information out. So what's our x bar? Well, according to the problem, it was 63.4 inches. So that was the mean of our sample of 200 women. Our critical z is based on the fact that we're looking for a 95% confidence interval. And if you recall, that critical z is 1.96. Our margin of error will be calculated as 1.96 times our standard deviation of the population over the square root of our sample size. So we can actually do that out. So let's do that. 1.96 times, we need a square root. Oh, sorry, no we don't. We need a 3.5 divided by the square root of 200. And that's going to give us a margin of error of 0.485. I'm just going to round that up to 0.49. I could have left this 0.85, but I'll make it 0.49. So the lower bound of our confidence interval will be our center, 63.4, minus our margin of error, which gives us 62.91. Our upper bound will be 63.4, our center, plus 0.49 to give us an upper bound of 63.89. So we can finally say that our confidence interval goes from 62.91 to 63.89. And now let's remind ourselves how we interpret these confidence intervals. So in this case, we are 95% confident that the true mean height of all women is between 62.91 and 63.89 inches. So there's our confidence level and our upper and lower bound. And again, notice that we're referencing the true height of all women because we're trying to represent that from our sample of women. So what if I told you that the actual mean height of all women is about 64 inches? Is this captured in our interval? So looking at the interval, we could see that no, 64 inches is going to be just outside to the right of our confidence interval. So it's actually not even in there. So the question then is, does this mean we did something wrong if our confidence interval doesn't actually capture the true parameter? Again, keep in mind, most of the time you don't actually know what the true parameter is, so this is just sort of a thought experiment. But I wanted to bring it up because the answer is no. Just because our interval didn't actually capture the parameter doesn't mean we did anything wrong in constructing it. Because it's a 95% confidence interval, that means that there was, from the beginning, a 5% probability that this particular interval would not actually capture our parameter. So any 95% confidence interval I make has a 5% chance of not actually capturing the interval, the true parameter. And that's what happened here. And that's totally okay. I just wanted to remind everybody that is the case. Now, if we made a wider interval, we'd be more likely of capturing it. And actually, if we used a z-star for 99%, we would actually capture 64 inches. So that would actually work. So one final note about confidence intervals for means. I hope at this point you've been thinking about what we've been doing enough to think about this question. How likely in the real world is it really that we would not know the mean of a population, but we would somehow know the standard deviation? That seems kind of strange that we would be missing one key bit of information, but somehow have another. And the answer is, it's not likely at all that we would know that information. However, when we do not know the population standard deviation, we can no longer use the normal distribution to perform these calculations. So a lot of what we're doing here would actually change. We're actually going to look at that situation next week when we don't know the population standard deviation. That's going to be a new topic. But this week we will assume that we know the population standard deviation so that we can use these methods. So I hope that was clear and made sense, and this should give you enough information to take on our practice problems this week.